And today we've got a fun identity that somebody just pointed out to me this morning, literally at 1 a.m. this morning, or at midnight last night. Uh, Somebody, Jay, shout out to Jay, friend of the channel, he pointed out this wonderful identity that 2025 is the sum of the first nine numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9. If you square that number, well, first off, let's write this in. So 1 plus dot 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 9 is 45. If you square 45, that is 2025. Turns out that that is also 1 cubed plus 2 cubed plus dot 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 9 cubed. Like, that's delightful. That's just delightful, isn't it? Isn't that so cool? I haven't seen this before. Have you seen this, Quasar? So Quasar says in the guitar channel, it's the square of 45. I didn't know this. So maybe this is old news to people, but I think that's so phenomenally cool. So here's our agenda today. Just for anybody, I think that that's a fun fact. Anybody, pretty much everybody remembers squaring numbers and cubing numbers. That's why I call it the... Also, one thing is a triangle number is when you add like 1 or 1 plus 2. They might be called triangle numbers because of this. Like if you write them out like this, I don't know. These are all the triangle numbers. 1 plus 2 is 3, 1, 2, 3 is 6, 1, 2, 3, 4 is 10, on and on. Those are the triangle numbers. And so this here is triangle 9, the ninth triangle number. So I call it triangle square. We've got a triangle number squared equals cubes, a bunch of cubes over here. So that's why I call it triangle square cubes year. All right, so that's fun. I'm going to literally show that to the kids that I tutor. But then we're going to go a little bit further. We'll revisit triangle numbers and the formula that we've proved in the last two streams. Coincidentally, yesterday I did a stream that was focused on proof by induction. So I'm going to be repeating some of that info. We'll just revisit that. And then what's so cool is that my friend texted me this formula and I was like, I'm pretty sure I've seen that. I actually proved exactly this formula just 3 days ago on the airplane when I was bored and on the airplane trying to just practice induction. So we're actually going to prove this identity. It's true not just for 9, but for any number n. The nth triangle number squared equals the cubes square, the sum of the cubes. So, well, I think we just did this first part. I'm going to go ahead and give that a check. And now let's talk about the triangle numbers just a little bit again. So this is like a review of what we did in the first stream. This is literally just a third stream, everybody. So this is 1 plus dot 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 n. And there's two really amazing, well, there's two proofs. I think that they're both amazing. I think that there's two really cool proofs of this. Proof 1. This one is magical, and I love to show this to kids because there's a great story around it. And then there's proof 2, and this is like a canonical proof by induction. So we'll use proof 2 to review what a proof by induction, how that works. A lot of people haven't seen this. Of course, most of you haven't seen my stream from yesterday. Of course, I wouldn't expect that. So, there's a wonderful story that when Gauss, who's a famous mathematician, he's one of the greatest mathematicians of all time, he proved a lot of beautiful results in number theory. Number theory is literally the study of whole numbers. All the numbers greater than one. They're the counting numbers, the simplest thing that everybody knows. But there are people who study number theory in and of itself. It's considered one of the most beautiful, pure fields of math. Some people say that it's the queen of mathematics, is number theory. So, Gauss did a lot of work in number theory as well as some other things. But the story is that when he was a kid, the teacher, whenever the class was acting up, whenever the class was getting rowdy, the teacher gave the problem, add all of the numbers up to 100. Go, practice. Like, stop being loud, stop being noisy, or whatever it was. Gauss found this phenomenal trick whenever he was a tiny little kid, apparently. You can write that, like, let's call whatever the answer is S for a sum, maybe. Then you can write it backwards. 2 plus 1. Then you can add both of these together. I mean, this is probably not exactly how he found this, and who knows whether or not the story is actually literally true or not, but it's what we tell undergrads nowadays. Every term, if you add them by columns, every term is 101. And, well, if you count, like there were 100 terms the first time around, 1, 2, 3, 4, 99, 100. So then this is 100 times 101 equals 2s. Therefore, 100 times 101 divided by 2 equals s. And you can calculate that that is 50 times 101, which is 50. So he found that in an instant, and then he went back to doodling or studying prime numbers or whatever he was doing instead of whatever the teacher... Well, you know what I mean. So that's the wonderful proof by insight. Like, it's a delightful, elegant, neat trick. It's just such a cool proof. But now it is also... This is a great... last thing, just for the just to finish this thought, is that the number 100 is not special here. The number 100 is not special at all. You can replace 100 with n, and then you have n plus 1 divided by 2. So this is the formula that we're going to prove a second way. This is the technique of proof by induction. So for people who weren't in the stream yesterday, which is everybody, you can think of dominoes. If you have a statement that you want to show is true for infinitely many cases, you can show that it's true for one of them, and then you can show that the distance between the dominoes is always small enough that if you hit one of them, then it will also topple over the next one. So that's like a nice way to say it. Basically, if you have a statement that you want to show is true, you can show that it's true for the first number. I use P to mean proposition here. You can show that it's true for one number, and then you can show that if you assume that it's true for a number, then it's also true for the next number. then you're done. Then you know one of them is true, and then every number, one of them is true, then therefore the next one is true, then therefore the next one is true, on and on. And so I have a quick, I think we can do this very quickly. We can do this. So in this case, the first part is considered the base case, n equals 1. Well, triangle 1, the first triangle number is literally just the first, is literally just 1. And then that is indeed 1 times 1 plus 1 divided by 2. So we're done. Next, we assume 1 plus ... n equals. So now we're going to assume the thing that we want to be true. And we can do that because we've shown that it's at least true for one number, n. So for some, you can think of it as like the last number that we've proved so far. And we know that there's at least one number, n equals 1, that it is true for. Then let's see what the next case is. It would be adding one extra term, n plus 1. Well, that, by assumption, the first part is n plus 1 divided by 2. And then we can add the second term. I'm going to go ahead and multiply it top and bottom by 2. If we expand these polynomials, then we get n squared plus 3n plus 2 over 2. And then that factors. N plus 1, n plus 2 divided by 2. This is exactly the statement for n plus 1. This is the formula that we wanted to show when you replace n with n plus 1. So that's dope. That's pretty cool. Like, it's a perfect canonical proof by contradictions. Okay, let's continue. And now, have you watched Star Wars? What a question. Yeah, absolutely. I love Star Wars. Who hasn't seen Star Wars? Cool. Any questions from the guitar chat or from anybody? Any questions? We can continue. Next. So we've revisited proof by induction, and now, with a tiny bit of time before I have to go really quick, let's prove 1 cubed plus 2 cubed plus ... n cubed equals I mean, this must be in a lot of math books, but I solved this from Andrew's number theory, exercise 1.1. Whatever, 5 or something like that. We're doing math today. Yeah. So I'm not always going to double stream, but today we are double streaming to guitar and math channel. This is exercise 2 from chapter 1, section 1. Yeah, so very niche, I know, but for some people, like myself, who are just absolute geeks, this is delightful, I think. And yeah, since you just tuned in, I'm proving this really incredible fact. 2025 is what I call triangle square cubes year. And that's because 2025 can be written in these two different ways. 1 plus 2 plus 3, ... 9, and then square it. Or 1 cubed plus 2 cubed plus 3 cubed, ... 9 cubed. Math. Yeah, I am a math with an A kind of person. Okay, so, oops, let's get back to this. All right, then, again, the strategy is base case. Usually, the base case is super easy. Like, is 1 cubed 1 plus dot 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 n squared? Yes. Done. Okay, so now we move on to the inductive step. Don't copy this verbatim for your math homework because this is gonna we're gonna be a little fast and loose, a little sloppy with this is not perfectly rigorous, even though it is pretty close. So now we assume. Yeah, I know math is boring for a lot of people. Echoes, but for some people, it's one of the most beautiful things in the world. For me, it definitely is. It's not for everybody, but so is same thing with classical music, right? So the statement with n plus 1 is we want to show that, which side did they do first? Yeah, the cubes. Let's do cubes as the left-hand side. 1 cubed plus dot 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 n cubed plus now the next term, n plus 1 cubed. Well, by hypothesis, we're going to assume that this first chunk is indeed 1 plus dot 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 n quantity squared, and then we add n plus 1 cubed. Recall that we just showed that the triangle number 1 plus dot 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 n is this. So let's square that thing. And then I'm going to go ahead and expand this n plus 1. That's going to be n cubed plus 3n squared plus 3n plus 1. Now we've got n squared times n plus 1 quantity squared over 4. Why don't we take this opportunity to get a common denominator on the two? 4n cubed plus 12n squared plus 12n plus 4, right? Now, n squared times n squared plus 2n plus 1, this 4n cubed, 12n squared, 12n, 4, all of this stuff over 4. Now I'm going to combine these two polynomials in the top. So all the n to the 4th terms are just n to the 4th. All the n cubed terms, we have 3 plus, like, right here we're going to get 2, and then here we're going to get 6. We're going to get 2 plus 4 is 6. N squared terms, we've got 1 and 12. N terms, did we lose one? Yeah, we did lose one right there. 12n, and then constant terms are just the number 4. All of this over 4. Now, I'm going to kind of take a shortcut because what we did was show that the left-hand side equals dot 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 equals this thing. What we can do is we can start from the right-hand side of what we expect, and if we can show that it equals the left-hand side, this thing that we found, and they can like kind of meet in the middle in a sense. So the right-hand side of the statement that we want to see is n plus 1 times n plus 2 divided by 2 quantity squared. That was ugly. There, let's just do it like that. So if we expand that out, we've got n plus 1 squared. We can do that. N plus 1 squared is going to be n squared plus 2n plus 1. And then n plus 2 squared is going to be n squared plus 4n plus 4, right? N squared plus 2n plus 1 times that. So again, I'm going to think in terms of the powers. So n to the 4th, we can get it from here, and that's the only way. We can get n cubed terms with this one and this one. So there's 4n cubed, and then 2 more n cubed by multiplying this and this. So we get 6n cubed. And now n, n to the power 1 terms are going to be 2n times 4. So there's 8, and then 1 times 4. That, did I miss something? Oh, wait, I went to n terms. I should have gone to n squared. N squared is going to be this guy multiplied with this guy. There's 4, and then 2n times 4n, there's 8, and then this one times this one, that makes 13 in total. You could do this a little bit more carefully by writing this as like n squared times the right-hand side, or the second term, plus 2n times the right, plus the second term, plus 1 times the second term. But at this point, you should feel fairly comfortable expanding to polynomials like this. So now n, 2n times 4 is 8, 1 times 4 is 4, so that is 12n. And now we have 1 times 4 for our constant term. And that is exactly the same thing that we got here. Therefore, left-hand side equals right-hand side. And so, assuming the statement at n implies that the statement is also true for n plus 1, and we're done. Happy, what is it again? Triangle, square, cubes year. Boom, done. Hell yeah.